Thank you for that very glowing introduction. One thing that Flip neglected to mention is that I actually have a visiting appointment here at UCR. So on my stray moments where I'm able to get away from teaching, I'm able to come here and hang out. So I'm really happy to be here and get the chance to talk to all of you. And I'm going to be talking about some recent work to look for hidden particles at colliders. And these particles are motivated by some of the deepest questions that are unanswered about our universe, which I'll talk a little bit about in the introduction. But I think that what's most exciting is the fact that evidence for these particles could be hiding unseen in data of experiments that we already have that could just be lying around. So I want to talk to you about where could these signals be hiding and what should we be doing to look for them. So to start, though, we have to talk about the gold standard of particle physics, which is our current theory, the Standard Model. And the Standard Model is essentially a complete picture of all of the matter that we can observe in the lab. It consists of the 3 non-gravitational forces and their associated force carriers, as well as 12 matter particles, which are organized according to what forces they feel. So the quarks, of course, feel the strong force. The leptons do not. The charged leptons, however, feel the electromagnetic force, and the neutrinos only feel the weak force. And then to complete the discovery of the Standard Model came with the observation of the Higgs boson in 2012, which was discovered in ATLAS and CMS at the Large Hadron Collider. And it's necessary for bringing all the pieces together, explaining why particles have the masses they do, and basically making the theory a self-consistent entity. So we have this theory that does a really good job of basically explaining all the particles and the properties that we can make in the lab. But there are several things that it doesn't explain. And these mostly come when we look outward. So the first major piece of evidence for new particles not in the Standard Model is the existence of dark matter. And when we look astrophysically, we see that galaxies like our Milky Way are actually embedded in this huge dark matter halo. And we know that the dark matter is there because it affects the rotations of stars and gases and galaxies. And it affects the motions of visible matter in lots of different length scales, from galaxy clusters all the way to the earliest snapshots of the universe. And if we look at what this particle can be, it can't be any of the particles that we know about because of various reasons, but essentially the fact that it's dark means that we don't see it. And it has to be stable on cosmological scales and all sorts of things. So you can go down the list and basically say none of the particles in the Standard Model could be dark matter. And there's actually about 5 to 6 times more dark matter than there is regular matter. So all the particles that we know about actually constitute some very subdominant fraction. And so as particle physicists, we want to know, what are these things? Do they feel forces like that are in common with us, et cetera? So this is perhaps a common motivation for physics behind this, beyond the Standard Model. But I also want to talk about sort of the dark side of the visible matter. So we're all made of something that to all of us probably seems very mundane, atoms made up of protons and electrons. But all of the particles in the Standard Model come with an associated antiparticle that has an opposite charge. So for instance, the proton has an antiproton that's negatively charged, and the electron has a positron that's positively charged. So looking around us, we can become confused about why is it that we seem to be only made of protons and not antiprotons? Why are we made of electrons and not positrons? And what this suggests is that at some point in the universe's history, there was some excess of matter relative to antimatter. And this excess is very tiny. It's about 1 part in a billion. But all of the antimatter annihilated away with all of the regular matter, and everything that we see is just this tiny little remnant here. So even the existence of the visible matter that we see, atoms all the way up to galaxies, is predicated on the fact that there was this excess of matter over antimatter. And the problem is that the Standard Model essentially puts these two things on very similar footing, so that we can't explain why there's more matter than antimatter. And so this suggests that there needs to be some new particles or new forces that allow for processes in the early universe to have this biased production of matter relative to antimatter and explain our existence. So really, when you see these charts of we don't understand 80% of the matter in the universe, we actually don't understand 100% of the matter in the universe because we don't know why we're here either. The last thing that I'm interested in is sort of another aspect of the darker side of the Standard Model, which is the particles known as neutrinos. These only interact through the weak force. And we know comparatively little about them compared to other particles in the Standard Model, precisely because they're so hard to detect. But there are a few things that we do know about them. The axis scale is a little bit hard to read here, but This plot shows the masses of all the particles in the standard model, ranging from the electron up to the Higgs boson. And this is in units of giga-electron volts. So this is ranging from about 10 to the minus 3 up to about 100, so spanning 5 orders of magnitude. But this break here represents 6 orders of magnitude, so bigger than this entire spread. And then way down here, we have the neutrinos. They're very, very light, and we don't understand why they're very light. And in fact, it's an even bigger problem than that, because the standard model predicts that they're exactly massless. And so our current theory can't understand what few properties we do know about the neutrinos, the fact that they have these small but non-zero masses. And in order to not disrupt other things, whatever new particles or interactions that are responsible for giving neutrinos mass need to talk to us very weakly. So all of these different things, I'm not going to have the chance to go into a lot of detail. I could give a dedicated talk about each of them. But they point to the existence of some new particles or forces that explain the things that we don't understand about our current theory. And essentially, these new particles are often referred to as hidden particles or hidden sectors because they need to interact with us very weakly in order to accomplish the phenomena that we observe, either for dark matter, the baryon asymmetry, or for neutrino masses. And so as a result, we expect these particles are neutral under all the known forces. And because they're neutral, their masses could be anything, ranging from very, very tiny to very, very large. And so in particular, they could be much lighter than the masses of the known standard model particles, and this affects the way that we might look for them. So in the past, it was fashionable to try and explain all of the unexplained mysteries of the standard model by adding 1 or 2 new particles. But in the most common theories that try to do that, searches haven't really turned up any positive signals. And so we can ask, well, are we missing anything? And when we look at the standard model, we see that this 20% of matter that's made up of the known particles is quite complicated, actually. There's a bunch of forces. There's a bunch of different particles that are charged under different things. So we can ask whether the new particles that explain these otherwise unexplained phenomena could form sort of their own little universe here, where you have maybe some dark Higgses, some dark forces, some dark particles. Okay? And there's no reason not to expect this. And the presence of these other particles both influences the cosmology as well as how we can look for them. And in particular, we want to know how they talk to us, so maybe there's some kind of a common force that mediates interactions. There has to be some way that we're talking to one another, at least through gravity and probably through other forces in order to explain the currently outstanding questions. And there are a lot of possibilities. Maybe we're actually all part of some bigger picture that we don't see right now because we're only filling in the details piecemeal. So right now, we don't actually have a lot of guidance. We have this motivation from cosmology, from a few particle physics experiments for new particles interactions, but we don't yet know exactly how they talk to us. So a natural question is, well, if we expect there are new particles, let's see how we can make them and test them in the lab. And one of the best and most precise ways of doing this is through particle colliders. And the reason why particle colliders are great is that they're very controlled experiments where you know exactly the energy and momentum of the particles, you smash them together, and according to relativity, you can break them apart and make other things. So what I'm interested in is seeing, okay, what can we learn about these open puzzles from particle colliders? And I'll talk about 2 sorts of classes of colliders, which are environments where we could be looking for these hidden particles and make sure that we can actually see them in the debris of the collisions. So the first of these types of colliders are proton-proton colliders, and the prime example of this is the Large Hadron Collider at CERN. And in these experiments, protons are smashed together, and you try to look for evidence of these new hidden particles in the debris. There's some advantages of proton-proton colliders, namely that the Large Hadron Collider is the highest energy collider that we've ever built. This means that if the new particles are very heavy and require a lot of energy to make, this is the place where you can do it. The downside is that protons are made up of quarks, which feel the strong force. And the strong force is, as the name implies, very strong. So every time you collide them, you get a bunch of mess, essentially, from radiation due to these strong interaction collisions. So for instance, here's a picture taken by the ATLAS experiment. You have the 2 beams that come in and collide. And you can see that each of these very thin lines, which are kind of blurred together here, is a particle that's made in the collision. So we're talking about hundreds of particles are made each time there's a collision. And what we're looking for are these very hidden, very potentially weakly interacting little blips in this mess. So there's some advantages and then some trade-offs that are associated with this particular strategy. The other extreme that we can go to is to say, well, let's not collide things that feel the strong force so that we have a cleaner environment. And there are colliders that collide electrons and positrons, neither of which feel the strong force. And when they annihilate, they basically completely vanish and turn into whatever the final state particles of the collision are from. And the picture on the left gives you an idea of a picture of a collision from the BABAR experiment. And you can see that you can count on 1 or 2 hands the number of particles coming out. So it's much cleaner, much easier to try and look for something. They also collide particles at a much higher collision rate than the Large Hadron Collider. So you just get more events. And so if you're looking for a 1 part in a billion or 1 part in a trillion effect that we might expect from these hidden particles, this is a good place to look. The downside is that the energy is lower. And so if you're making a heavier particle, then you may just not have enough energy to actually create it in one of these colliders. So they provide complementary functions. And as Flip mentioned in my talk, I'm going to focus on a particular class of hidden sector particles because I think that they're the most underexplored, have the highest potential for discovery, and are one of the most generic predictions to come out of these different hidden sector motivations. These are long-lived particles, and I'm always wary in physics when we talk about high energy, low energy, long-lived. It's always relative to something. So a long-lived particle for us is something that travels a macroscopic distance before it decays. And in the machines that I'm talking about, macroscopic distance means about 10 microns. So I produce it in some collision. It travels some distance, which is going to depend both on its lifetime, which is an intrinsic property of the particle, as well as the kinematics, the boost of the particle. And then it goes some distance and decays. And we're basically saying this is some detectable distance according to the resolution of our detector. So in the rest of my talk, I'll hopefully convince you that these are well motivated, that they pop up generically in the kinds of solutions to the outstanding problems I mentioned before, and then talk about why they're hard to see experimentally and also present potentially a spectacular signature of new particles, and then what are the ongoing efforts to look for these particles. So in the rest of my talk, I'll talk about the motivation of why these kinds of particles we expect. I'll talk through some of the work that I've been doing to expand the searches for these particles at the Large Hadron Collider, both at the sort of general purpose detectors as well as at a specialist detector, which is called LHCB. And then finally, some work that I'm doing actually as a member of the BABAR experiment, doing analysis with real data to try and uncover evidence of these particles. This experiment stopped running over a decade ago, and yet we're finding that it could bring orders of magnitude improvement to our understanding of the existence of these particles. Long-lived particles, why bother with them? Okay, well, the first one is just a phenomenological perspective, which is that the standard model has a lot of long-lived particles. So we use this expression LLP a lot just to shorten long-lived particle. The x-axis shows the mass of a bunch of particles in the standard model, and the y-axis shows the lifetime, which I multiplied by c to give a distance. And this is if something's going a reasonable fraction of the speed of light, how far it would go in an experiment. And you see that the known particles span, some 20 to 30 orders of magnitude of lifetime. So long-lived particles are just a fact of life in the standard model. And if I were to draw some distances that correspond to the geometric size of our detectors from the resolution of the detector up to sort of tens of meters, which is about how big they are, it cuts some swath of particles here that are long-lived particles within the standard model. And there are a few things that we can learn from this picture. One is that there's some slight correlation that as I go to higher masses, I find that there's a shorter lifetime. Okay? And we'll see in a moment why that is. The second is that if I look at the standard model, because of this, the highest mass long-lived particle is a B meson, which is made up of bottom quarks, and it has a mass of 5 giga-electron volts. So then there's this big gap here, and so if I discover anything new up here, it is basically really hard to fake with any of these particles down here. So it provides this nice open territory where if we look for long-lived particles in this range, then it would be a really spectacular sign of something new. Okay. Now, why are these particles long-lived? Well, let's take a look. So here's an example of a particle that's long-lived. It's a charged pion, which is made of an up quark and an anti-down quark. And when this particle decays, what's actually happening is the quarks inside annihilate. And in order to conserve charge, the only force they can annihilate through is the weak force. So they go through the carrier of the weak force, which is a charged W boson. And they decay into, say, a muon and a neutrino. And so there's some features of this that we see. So first of all, there's some dimensionless number that characterizes the strength of the weak interaction, which we denote as G weak. And every time there's an interaction, we pick up one of those dimensionless numbers. If we plot the decay rate, which is the inverse reciprocal of the lifetime, we see that it depends on the square of the amplitude associated with this process. And so we got 4 powers of this dimensionless number. But then we get this ratio of masses. And this follows from the fact that this W boson is very heavy, about 100 giga-electron volts, and this pion is very light, about 0.1 giga-electron volts. And this process is very rare because essentially you don't have enough energy to directly create this particle, so you have to sort of indirectly create it in some quantum mechanical process, and that allows this decay to proceed. So we can look at these numbers. This dimensionless number to the 4th power is about 0.2. It's not too small. This ratio of masses is about 10 to the minus 12. It's very small. So we see that because the pion is light compared to the W boson, I get a ratio of masses to the 4th power. So even though they're not that far apart in mass, I get this huge power suppression of the decay rate and consequently enhancement of the lifetime. And for a lot of the particles that we see in the standard model, this is exactly the hallmark of them. If I ever have a couple of particles and they have mass ratios that are not exactly order 1, you very naturally generate these long-lived particles. And if we think back to the sort of hidden sector example that I showed, where maybe we have multiple particles, if there's any difference in the mass of those particles, you're automatically going to get long-lived particles out of them. So here's an example of a hidden sector particle that is well motivated by the outstanding question of the standard model. I'm calling this a dark neutrino or a sterile neutrino. It's some new particle that interacts with the regular neutrinos in order to explain their mass. And this dark neutrino does not directly feel any of the forces. It's a hidden particle. But it can mix with the regular neutrino. Essentially, the interaction and energy eigenstates of the theory are not aligned. And so if I produce some set of interaction states, they can oscillate from one to the other. And that mixing occurs with some small number, which is the mixing angle theta, which parameterizes the misalignment of these states. And so we can see, okay, well, what's the lifetime of this hidden neutrino if we're able to make it? Well, if I have an ordinary neutrino, it feels the standard model weak force through the same kind of process we had before. It goes through a W boson into, say, an electron, an anti-muon, and a muon neutrino. But because this regular neutrino mixes with the hidden one, this allows the hidden one to decay. So I can start with a hidden neutrino and mixes into the standard model neutrino and mediates this process. And the scaling will be exactly the same as we had before. I have some powers of this GW to the 4th power, which is only about 0.2. It's not a very small number. I have this theta E squared, which could be a small number. And then I have some ratio of masses to the 4th power, which could also be a small number. And so if we actually calculate what the lifetime of this particle is in order to explain the standard model neutrino masses, we find this interesting coincidence that here's the mass of the particle in giga-electron volts. Here's the lifetime. This time it's in millimeters, but I've once again plotted the collider distance scale. And we see that if this particle explains neutrino masses in the range that's accessible at particle collider experiments, like the Large Hadron Collider, it's automatically a long-lived particle. And so we can directly map explaining the neutrino masses onto this prediction of this class of particle that we can see. So this is sort of a phenomenological argument. I'm not really talking a lot about the theory here. It's mostly just, okay, based on what we see, we expect there to be long-lived particles. But it turns out that we can make a more direct connection, which is that long-lived particles also follow from the cosmological motivations for new particles that I talked about at the beginning. And one of these that I want to talk through briefly is the example of generating a matter-antimatter asymmetry. And this problem is near and dear to my heart, in part because I feel like there's lots of interesting theories that could go into trying to explain this and leading to very particular phenomenological predictions. But we can ask, how do I end up with more matter than antimatter? One way you can do that is by taking a particle that decays into a set of quarks, and then the same particle can also decay into a set of antiquarks. You can say, well, how do I get more matter than antimatter? We'll just make this particle decay more often into quarks than into antiquarks, and then you're done. So I'd say, okay, sounds pretty easy. Cook up a model where I have some new particle, some new force, decays more often into quarks than antiquarks, and you're done. The problem is that quantum mechanics allows things to happen in reverse. So I can reverse the process, and I can have a set of quarks that annihilate into this particle, or it's the same set of antiquarks annihilating into the same particle. And if you have a system that's in equilibrium, like in the early universe, forward and reverse rates become equal, and you end up not generating any net asymmetry because basically whatever excess rate is associated with the production of quarks will turn into an excess inverse rate that destroys them. And so you don't get any asymmetry, which sucks. So what can we do to actually keep the asymmetry? Well, we can note that this inverse process doesn't have exactly the same rate as the forward process. In particular, if this phi particle is very heavy compared to the quarks, then this process can only happen if the quarks have enough kinetic energy to go into the phi state, whereas this forward process can always go forward. And if the typical temperature or energy of the quarks is insufficient to produce this phi, then this process is Boltzmann suppressed. And what you can get is a suppression of the rate that destroys the asymmetry and just have this forward process that creates the asymmetry. So we need something that's going to essentially hold off on this phi particle decaying until the reverse process is very suppressed. And so how can we do that? Well, the thing that's changing the typical energy scale of particles in the universe is the expansion of space-time. If we just wait long enough, then all the particles in the Standard Model have cooled enough that this reverse process turns off. Then we let phi decay, and we just get a large asymmetry. So this is the simplest way that we can satisfy this out of equilibrium condition. And it provides a way of quantifying how long-lived this phi has to be so that it waits to decay until all of these inverse processes are shut off. So the decay rate of the phi needs to be shorter, needs to be less than the expansion rate of the universe. That's the sign that the universe has lived long enough such that the temperature has dropped below when the destruction processes happen. And so this just now becomes a question of numerology. You can just calculate how long-lived does this particle phi have to be. And you can find that if it has a mass of 100 giga-electron volts, its lifetime has to be about 50 picoseconds, which if I multiply it by the speed of light, gives me about 1 centimeter traveling distance. So this is something that came out of some models that Jano worked on and that Jano and I worked on the phenomenology of back in the day. But it's sort of an interesting fact that the out of equilibrium condition of the early universe tells us that if you have weak scale particles, that the lifetimes are typically going to be long. Okay, that just follows from what the expansion rate of the universe was at that time. And it's also kind of cute that the size of the universe was essentially about a centimeter when the temperature was at the electroweak scale. So that the typical size of the doubling of the universe is something that we can actually see in the lab. It's not astronomically huge or very, very tiny. So now there are lots of ways you can get around this, but it is interesting. One of the ways I got working on long-lived particles is that it seemed like every theory I was working on involving low-scale, sort of within reach of experiments, baryogenesis or dark matter was pointing towards long-lived particles. So there is this kind of cosmological connection there. Okay, so now we want to see how we can look for these at colliders. And so how can experimentalists look for the particles? Well, so I've shown here a cross-section of the CMS detector, which is one of the general purpose detectors at the LHC. Perhaps you've seen something like this before. But the detector, it's a cylinder, so it covers the whole solid angle, or as much of the solid angle as possible. And then it's made up of different layers that respond differently depending on the particle passing through. If it's charged, if it feels the strong force, if it doesn't feel any force at all. So for instance, the muon, which feels only the electromagnetic force and is quite heavy, moves all the way through the detector. And it's in some sense the cleanest thing that you can see because you can pick up its signals at every point through this entire multi-10-meter long detector. Whereas things like the electron, they curve in a magnetic field and hit something and deposit their energy there. And the whole point of this is that by adding together all this information, you can measure the momentum and the energy of the particles coming out of the collision, as well as identify what they are. Now, this all seems good until you notice that all of these pictures are showing the electron and muon coming out of this collision point. Whereas if I draw a picture of a long-lived particle, what I have is it goes through the detector undetected and then decays at some random point inside of the detector. And that's not what the different layers of this detector are meant to do. They're all meant to be looking from things coming out of this collision point. And on the one hand, again, this could be very spectacular because this isn't really something that standard model particles do. But it's also a problem because unless you have a dedicated reconstruction of these particles, they're going to be missed by the default algorithms. So what can these particles look like? This is a nice cartoon made by someone on the ATLAS collaboration of all of the different things, or some reasonable set of the different things that long-lived particles can do. They can leave tracks in the inner detector and then disappear. You can have things that sort of emerge out of nowhere. You can have isolated particles that emerge out of nowhere. You can have groups of particles that emerge out of nowhere. You can have sort of nothing and then blasts of energy in different parts of the detector. You can have things coming out of the outer parts of the detector, which is where usually only muons would be hitting. So again, this is exciting because these are very weird things to see. This isn't what you typically see in your collider environment. But there's also a lot of crap in the collider environment, as I saw. There's just stuff going everywhere. And if you're not specifically looking for it, the events might not be reconstructed, or even worse, they might not even be recorded to tape. And the reason for that is that there are about 30 million collisions per second at the LHC, and only about 1,000 to 10,000 of them can actually be recorded. So the data that we get is only 0.000 or 0.001% of all of the collisions that are happening. And the reason is that most of it are just strong interaction, glancing collisions that release a bit of radiation and are not that interesting. So the way this is handled is through something called a trigger, where basically on the microsecond to millisecond time scale, the detector takes a quick readout. So perhaps this is what actually happens in the decay. You have some particles, you have some long-lived particles. But what the quick peak of the detector does is it just looks for depositions of energy or hits in different parts of the detector. And based on that information, says, is this something I'm going to keep, or is this something that I'm going to let go? And it can do some amount of sophisticated reconstruction, but only on a subset of the events. And so it could be that this interesting collision just looks like something where you're like, oh yeah, there's just some strong interaction crap that hits various parts of the detector, and I'm not going to keep it. Whereas if you can keep it, then you can run more sophisticated algorithms and actually back out all of the different features of it. And so a kind of ever-present question is not only just how would we reconstruct it, but how are we going to record the data? How are we going to make sure that it's there? So to give some concrete examples of what some of the missing discovery potential could be, I want to talk through some examples, one of which is this dark neutrino that I've already introduced earlier. And I want to start by saying that long-lived particle searches at the LHC are happening. They've been happening since the first day of the experiment. And they've typically been motivated by supersymmetry or new particles that are quite heavy. And they often rely on triggers and reconstruction methods that are more conventional, basically that there's just so much energy that it passes all these trigger thresholds anyway. So the question is, what could we be missing in those searches? So in this example of a dark neutrino, remember we have a regular neutrino which mixes into this new particle. And I argued that this new particle can decay through the weak interactions by mixing with the regular neutrino and then interacting with the W boson. Well, through the same process, you can also make this hidden neutrino. So I can make a W boson through a weak interaction at the LHC. It can decay into a regular neutrino, which mixes into the hidden one. It goes some distance, mixes back, and then decays. And so this gives us a very firm prediction in these models about how are they produced and how could we be looking for them. Okay. So this red box here indicates this picture on the left. So this is the long-lived particle process, and then the other parts of the diagram illustrate the production process. So this is something that, like I said, it just automatically happens. There's a prediction for long-lived particles, so how well do existing searches do? And the answer is that basically none of the existing searches are sensitive to this. And the reason is that the W boson has a mass of about 80 giga-electron volts. It's divided up amongst 4 particles, so each of them have, on average, 20 giga-electron volts. And that's a very low compared to, say, some of the most spectacular signatures that you can get. And essentially, all of the things that look for long-lived particles that decay to muons or electrons, their thresholds are too high to actually catch any of these events. So we need to try something new. And what the theory motivation tells us is that in addition to this long-lived particle in the box, there's this other particle here, which comes from the decay of the W and is not long-lived. So this is something that the detector will always reconstruct well. It's coming from the collision point, like the detector is designed to do. And then in association with it is some long-lived thing. So what we can actually see is something like this. There's a collision, it makes a muon that goes off, and then there's the long-lived particle, and then it decays into a bunch of stuff. And by tagging this particle, you can record the event to tape, and then try and look for these other long-lived leptons offline, and use that to reduce the backgrounds enough that you can discover it. And so this plot shows some projections that I did a few years ago looking for how these searches could improve upon this well-motivated signature. The blue range indicates the long-lived particle search sensitivity. And this is with 300 inverse femtobarns of data, which is about twice the current data set. So this is about maybe here is what we could currently do, which is a couple of orders of magnitude better in rate than is currently doable. And so this is something that's not being caught currently, but could potentially be caught. So there's also a line here that I'm not going to talk about because there's a part where it's not a long-lived particle and it decays quickly. The CMS experiment's actually done a search for this for the non-long-lived case, which is a little bit easier. And it currently has the best sensitivity of any experiment to these models. So this is actually something that there is a real improvement that you can see in an actual publication. The long-lived search is ongoing, both by CMS and the other experiments. So here's an example of a gap that could potentially be filled in. Here's another example, one that instead of being motivated by neutrinos or the baryon asymmetry is motivated by dark matter, is that maybe this dark matter has its own dark forces. Just like we have electromagnetism, maybe dark matter has its own electromagnetism. And this particle can actually talk between us and the dark matter through a mixing that's similar to the one that I've been talking about. Now, if dark matter just has a massless photon, that can run into problems because there are cosmological constraints on new light particles. And if it talks to us with sufficient strength, there might be a lot of it, or it would show up, for instance, in anomalous cooling rates and stars or in supernovae and various things. So in a lot of the models, this thing has to be not massless, but actually have a mass. This then suggests, well, maybe it has its mass through a Higgs mechanism. So in this toy model of a hidden sector, we have a dark photon, which is the carrier of the dark electromagnetic force, and a dark Higgs boson, which gives a mass to the dark photon. And just like in the standard model, where the regular Higgs talks to the Z and W bosons, this dark Higgs talks to the dark photons. Now, this dark photon is neutral, and it also can mix with the observed photons and Zs, okay, through a similar kind of mechanism where there's a misalignment of the propagation states and the energy eigenstates. So in quantum mechanics, we can get this sort of mixing relatively easily. And so what this means is that every time we could make a dark photon in a process, it's also possible that you'd make one of these other particles. So this gives an interaction between our particles, the dark photon, and the dark Higgs. And this leads to kind of interesting signatures that you can have. For instance, a standard model Z boson mixes into a dark photon. It decays to a dark photon and a dark Higgs. The dark photon, in turn, decays to this mixing back into a regular photon into particles we can see. And the dark Higgs talks to two dark photons, and they also go back. So this is something that is, again, actually quite a striking signature. You have a Z boson, which decays into like 6 particles. This is very rare in the standard model. It can happen quite commonly in these new hidden sector theories. And so the question is, how do we look for this? Well, it's tough again, because the Z boson mass is about 90 gigaelectron-volts. 90 divided by 6 is about 15, I think. So that's even smaller than the average energy of the last signature we're talking about. These are things that will be produced all the time at the LHC, but you have to try and actually pick out these very low momentum particles in the mess. Okay. So there's a similar story. Current searches of the LHC are not sensitive to this. We once again can get a long-lived particle from the fact that if this dark photon is a little bit heavier than the dark Higgs, we have mass ratios that suppress the decay rate, and we can get a long-lived particle very easily. Just like in the other case, we also have some other stuff that comes along for the ride that's not long-lived, and that could potentially be well reconstructed by the detector and used to catch the event. So once again, we have something that emerges out of the collision point, a mu plus and a mu minus pair. Then I have a long-lived particle which travels some distance and decays to a bunch of stuff. So I can tag this and use it to record the events and then try and discover this extra long-lived particle here. And so this is something I worked on a couple of years ago. And once again, what we found was that, so this plot shows the dark photon mass. This shows the mixing. This is with 40 inverse femtobarns. So this is about a third of the current data set. And already you can improve by up to an order of magnitude depending on the mass of the dark Higgs and the interaction strength of these particles over current sensitivity. But it's something that just wouldn't be found in current searches. So I could go on like this for a long time. I'm not going to bore you with endless models. I think the big picture point of view is that there are a lot of ways that these searches can be improved where there are well-motivated models that are flying under the radar. And what's also interesting is that they seem to be pointing towards some common themes about how we can try and improve systematically our search strategies. So some of the common themes are the hidden particles decay as a long-lived particle. So that's one thing. they tend to come with something else, so some other associated object, which depends on which theory you're looking at, but there's a limited range phenomenologically of what these things could be. It could be an electron, a muon, it could be something invisible, so on. And then in many cases, we also get high multiplicities of particles in the final state. And so we can try and collectively use all of these things to say, well, let's look for something that's striking enough that it gets us onto tape and that we can beat down the noise from all of these very busy, strong interaction processes. So this informed a lot of the subsequent work, which is moving away from individual models and saying, how do we, with a minimal set of searches, cover as much territory as we can of this very vast but well-motivated parameter space? There's one last subtlety that I need to discuss before I get into what are the efforts to actually figure things out, which is that I've been saying in a somewhat cavalier fashion, yeah, the searches don't cover this, or they do cover that. And it turns out that it's actually not obvious when an existing experimental search applies to a theory. And the reason is that these are non-standard objects that the experiments are reconstructing, and they're using some specialized algorithms to find them. But that makes it hard for people outside of the collaboration to see whether or not, if you have a theory, if it would be caught by that updated algorithm, or if it would still be missed. So as an example, the work that Yano and I were doing, we were interested in this question that the CMS experiment had to search for a long-lived particle decaying to 2 quarks, which looks like this. Collision point, it goes some distance, it goes into 2 quarks. The fact that there are 2 quarks is really important because momentum conservation says that if I add up these 2 quarks, they fall along the original momentum direction, okay, which you can measure from where this decay is happening, that vector in this particular way. We were interested in a theory where this particle decays to 3 quarks, where if I add any of these 2 quarks, they may or may not actually line up along that way. And their algorithm had baked into it the kinematics of the 2-body decay. So we didn't know, and actually there were theory papers at the time that said there's no way that we can know, and we have to pretend that this search doesn't apply because we just have no way of calculating it. So we did a lot of work, and I will spare you the details, except we found that actually the search does apply. We basically had to try and implement the algorithms that they were doing, and what we found was in spite of the inaccuracies of our modeling, we were able to do well enough to show that it was at least covering these signatures to some extent. But this was a lot of work, and this is not necessarily very rewarding work either, because you're trying to guess at what the experiments are doing, we're talking to the experimentalists, and if we had to do this for every theory, it would be very impractical. So in terms of the long-term legacy of these searches, we have to ask not only how are we doing the searches, but how are we presenting these non-standard things in such a way that, me, because I'm lazy, I don't want to have to do this, but also people of future generations who can't just call up their experimentalist friend and ask them questions, that they'll know whether or not the search is actually applicable or not. And this is something that we want to avoid. So this led myself and a few other people to form a community that brought together experimentalists from all of the LHC experiments as well as theorists to try and see what the best path forward was. Basically, we're dealing with an incredibly vast parameter space. So what are the most well-motivated things that we should be looking for? And are there ways that we can design searches to be maximally inclusive so they cover as much as possible while still having the power to actually see a signal? We want to map this sort of theory signatures onto actual realistic searches that can be done and take advantage of the incredible technology that's being deployed in these experiments. And then working with the experimentalists to actually make sure that the searches happen, providing sort of moral support as well as the theory support in terms of simulations and suggestions of how to proceed, and providing the tools that are needed to basically have these searches happen. So this community had its first workshop in spring of 2017, and we've been having semi-annual workshops since then, as well as working on a community document that just came out last month. So what were the things that we focused on? Well, what we wanted to do was try and identify the highest impact things that we could be looking for in the best way of organizing these long-lived signature spaces. So we worked hard to develop a minimal complete, which is in quotation marks, because nothing's ever complete, but what is a set of models that cover as much of the basis as possible that allow us to see what signatures we can cover with the searches. Using this minimal set of models, we could synthesize the current coverage from the order 20 or so experimental searches to identify where are they effective, and therefore we don't need to push on it anymore, except for just repeating it with more data or perhaps better instrumentation with the upgraded detectors. Where there are gaps where there's basically no coverage, so in this sort of mass cross-section plane or lifetime plane, where do we have coverage, where do we not? And what new searches could we do to try and fill in those gaps? And then recommendations to how you can generalize the searches and present the information so that everyone in the community, both theory and experimentalists, can interpret what the searches are doing and how they impact whatever they're looking for. There's also a bunch of forward-looking things in terms of what are the studies that we can do in terms of the upgraded detectors that are going to come with the big upgrades that are happening to the LHC, both at this current shutdown and the next shutdown. Providing tools for making sure these searches happen so that experimentalists aren't scared off by the fact that they don't know how to simulate the signals. And then what are the things that are not being covered by our sort of incomplete but best first attempt to characterize the signatures, and what are things that we can be doing to look for them. So this is only just the beginning to realizing the LHC potential. There's a long way to go, but it's an exciting start. And as Flip mentioned, I think it's a great place where if you either just want to know a little tidbit of information or you're actually interested in seeing what the current status is, you'll be able to take a look at. The disclaimer is it's about 300 pages, so you don't want to read it from front to back. Some developments that have happened in the last few months, they're sort of the first searches that are starting to use these methods of a long-lived particle in association with something else. In this case, they were looking for a dark Higgs boson decaying to a Z boson and a dark photon, and they used this quickly decaying Z boson to trigger and tag the event, and they currently have the best sensitivity in this particular set of models. So this is a very narrow application of a search, but it's one of the first attempts at actually implementing these ideas, and there are many more that are in the pipeline. In the last 15 or so, 20 minutes, I want to talk about what are other ways that we can be going with looking for long-lived particles, particularly some directions that are currently underexplored. So the first one I want to look at is the LHCB experiment. Everything that I've said so far is applicable for the general purpose detectors, ATLAS and CMS, which are basically giant cylinders with end caps that try to get as many particles coming out as possible. But LHCB is an interesting experiment. It was designed to look for long-lived particles in the Standard Model, in particular these B quark-containing mesons. And it has an interesting configuration. The collision point happens over here, and the detector kind of forms a cone off to the side. So it's only capturing particles that come out of the collision in this direction. It covers about 1 to 15 degrees around the beam. And this is just because the way that B mesons are produced are preferentially with a big boost, and so they tend to go in the forward direction. So one problem or difficulty with this experiment is that if I have long-lived particles that are going over here, they just won't make it into the detector. And so that's one reason that it's been understudied, is that people say, well, if I'm looking for a rare process, I want to look for it in all directions. The other thing is that it only has about 5% of the collision rate that ATLAS and CMS have, and that's just to avoid having their instrumentation fried by the collision rate, that for their physics goals, they don't actually need to be going faster than that, at least at the moment. Now, what are the benefits of LHCB? Well, they're moving to a system that's called triggerless readout in 2021. So remember that one of the main sticking points is that we need to somehow record the events, and we're only getting this sneak peek at the detector, and we can't actually resolve everything. LHCB is upgrading their electronics so that they will be able to reconstruct every collision at the full amount that it would be reconstructed offline in real time. So they would get the full picture immediately. This doesn't mean they can record every collision, but it means that at least when they're deciding which ones to keep and which ones to throw away, you can look at the whole picture. And this is something that can be programmed in progress so that if there's some new idea of a hidden particle that we hadn't thought to look for, we can put it in. It also has the capability to read out parts of a collision. So if you know there are particles that are not interesting, it can just pick out those parts, and because it's only reading out a little bit of data, it can do it for more collisions. So some examples that I'm working on, actually there's a paper that's coming out tonight, on what are some things that LHCB can do that can't be done in other experiments. And one is the discovery of essentially a muon atom. This is something called true muonium, and it's a standard model particle, so we know it basically has to be there. And it's a bound state of a muon and an anti-muon, which are attracted by the electromagnetic force. And this is something that's never been seen before, and because its properties are predicted by the theory of electromagnetism, it can potentially be a probe of our understanding of electromagnetism. Now, these muons are orbiting around each other, but occasionally they'll bump into each other and annihilate, and they'll typically annihilate into an electron and a positron. If you calculate the decay length of this particle, it's about 0.5 millimeters, so it's in our range of something that's a long-lived particle. And so what we're looking for are long-lived electron-positron pairs. And it has this other weird property, which is that this is not an elementary particle, it's a bound state, and if it hits material, that material can impart enough energy to exceed the binding energy and split them into a pair of muons. And so what you find is this is a picture of the radial decay position of the muonium, and this is the probability of its decay. It travels out some distance, and then it plummets. And that's just because there's some material in the detector, and as it passes through the material, it splits into muons. So what you see is a long-lived particle that exists only in the inner part of the detector and never in the outer part of the detector, which is a very striking signature. And what we show in this paper is that you can actually discover it in the next run of the LHC, but this is something that you couldn't do without the triggerless readout because the momentum of these electron-positron pairs is so low, they would never pass the trigger. But now we don't really have a trigger. You can just reconstruct the event, and you know what the mass of this particle is. It's about twice the muon mass, and so you can just pick out pairs of electrons and positrons that have this property. And this allows you to actually discover this particle that's never been able to be discovered before. Another thing that you can do is basically this triggerless readout is useful anytime you have some weird decay that doesn't happen very often. And so for instance, if you have a hidden particle that decays to a muon and a pion, this violates a bunch of the symmetries of the standard model. You can just look in, and anytime you see these two things coming out of the same place, you can just grab them. And so anytime you have some strange set of things, that's good. Of course, you have to program that set of strange things in. And so there's a lot of theory work that needs to be done to figure out which things are there to do. It's a low-energy hadronic physics that can be quite complicated. And indeed, you have to do the theory correctly. And so one of the things that I did with Michael Peskin a few years ago is that we noticed that LHCB was not doing their theory interpretation correctly for one of these exclusive decay things, and they were not having the sensitivity that they thought that they did. And so there's a lot of work that is ongoing in order to maximize the applicability of this particular strategy. Okay, last, we can move away from the LHC down to lower energy experiments, and I want to talk a little bit about what I'm calling hidden sector archaeology, basically digging through old data sets to try and look for these evidences of new particles. So why? Well, the LHC, there's only so much that it can do. It is, at the end of the day, kind of a busy, messy place. And so if we're looking for particles that are produced at lower energies, then it makes sense to just look at a lower energy collider. And the experiment that I'm part of is something called the BABAR experiment, which was an electron-positron collider at SLAC that ran from 1999 to 2008. And it also was meant to study B mesons, which also have a lifetime of about 0.5 millimeters. So its instrumentation is optimized for looking for these long-lived particles that potentially could be hidden sector particles. What I find also interesting is that this is a particle collider, and anytime you collide particles together, you can make new stuff. Compared to the LHC, there are very few searches for the production of new particles. And again, this is in part due to the theory bias that said all new particles are 100 GeV out of the range of this collider. But if you're looking for hidden particles, they can have whatever mass you want them to be. And so you can just make them as copiously at this experiment as you do at the LHC. And what's especially interesting is that when BABAR does do one of these searches, it basically has the world's best sensitivity to them. So many of the leading sensitivities to hidden particles in dark matter models comes from this BABAR experiment. So you can say, well, what else could be hiding if we have few searches and yet these searches are really powerful? So it's a great opportunity for new and creative ideas. And it's also exciting because this is a successor experiment to BABAR in some sense, a similar type of experiment called BELLE just started taking data. Last year, the commissioning run, and this year, we'll be taking data, first data with physics, and it's going to accumulate of order 100 times more data than BABAR. And so it's something that will rapidly be an expanding field of looking for these particles at low energy colliders. There's actually very few searches for long-lived particles at BABAR and at its competitor experiment. There is a very nice search. It's looking for a boson decaying to a pair of particles, like electron, positron, mu plus, mu minus, e mu, pi pi. And this plot shows the limits on the production cross-section and whatnot. So it's very nice. It's a model-independent search. And the problem is it's somewhat limited because they were looking for two particles that emerge from the long-lived thing that's decaying. And so there were actually a reasonable number of noise coming from random crossings of particles and misreconstructions and so on. And this search is actually insensitive to anything that's a fermion because all of these things have even spin. So if you have a hidden sector particle that's a fermion, it doesn't apply. If you have a three-body decay, it doesn't apply because it reconstructs the invariant mass of these particles and so on. So there's actually a huge range of possible searches that could be done in analogy with what the LHC is doing. To give a sense of what kind of sensitivity we might be able to accomplish, this is a plot that shows a particular model where I have a dark photon which decays to some long-lived particles that in turn decay back to the standard model. And you can ask, well, what kind of sensitivity might we expect with, say, this BELLE-2 experiment that's coming online? And this shows the mass of the particle in the lifetime. And this lifetime spans 6 or 7 orders of magnitude. So it's not like we're honing in on some very specific lifetime. And the mixings that we're sensitive to can be as low as 10 to the minus 5, which is orders of magnitude below the best sensitivity of other experiments to this kind of particle. So because of the huge collision rate and the very clean environment, depending on the signature and how you suppress the backgrounds, you can actually accomplish huge improvements in sensitivity to these particles. And I'm doing ongoing theory work to try and figure out what the best signals are, how do you suppress the backgrounds, and so on. So the problem with BABAR is that it's old, and there are very few people working on it now. And so I had some ideas for things that they could do, and one of the experimentalists said that basically if you want to see it done, you have to do it yourself. So I joined the experiment, which has been really fun because basically normally theorists aren't allowed into the data of these experimentalists, and basically I've been able to do whatever I want with it, which is very fun. So as an example of something that I've done, which is not a long-lived particle search, some force that couples preferentially to heavy flavor leptons, we did the first direct search for this particle in the mass range that BABAR is sensitive to, and are essentially able to exclude some parameter space that's motivated by anomalous measurements of muon properties and have the best sensitivity of any experiment. And there's several ongoing searches that I'm doing, including a long-lived particle search, that should have improvements of sensitivity up to 4 orders of magnitude in rate over the current ones. However, this one is public and those ones are not, so I can't really talk about them, at least not while I'm being videotaped. But I think what's also exciting about this is that there's a lot of opportunities for theory-experiment crosstalk, that the more that people in the theory community learn about the challenges that are facing these experiments at the detector level, then that helps us think about what kinds of signatures we could be looking for and how to improve the searches that we have. So to conclude, I think that there are really great motivations for these new particles, in particular that a lot of them are pointing towards long-lived particles. The payoff is potentially huge, but the signals are very challenging. The real benefit is that these experiments exist and that the data exists in many cases, and we can actually just look for it, but it requires a lot of effort. And so I've been involved both on the side of trying to figure out what these signatures are and also the kind of efforts that are required to actually mobilize the community to make sure that these things are done. And of course, this interfaces with lots of different approaches, many of which are being done here in terms of using cosmological probes, astrophysical probes, small-scale experiments, and so on. And the hope is that by bringing all of these things together, we'll be able to, in the next few years, make some progress on what these hidden sector particles are or aren't. Thank you. Questions? Yes.
You show all these particles as coupling to normal particles, now that we know already. So when we are at LHC and produce the heavy particles like the Higgs,
Yes.
shouldn't these new channels basically affect the width of those particles?
They can. So for instance, one of the reasons why the Higgs is so exciting in terms of its sensitivity to these hidden particles is that the dominant decay is to bottom quarks, and the coupling of the Higgs to bottom quarks is very small. So the width of the Higgs is many orders of magnitude smaller than the resolution of the detector. And there's sort of inventive ways of constraining the width of the Higgs. But currently, the best measurements are of order 1 multiple of the Higgs width. And so actually, the Higgs could have a huge decay to these other particles. So So for the Z, there is as well. So I guess I would say that the Z width measurements are like an irreducible constraint, that you can't get away from them. Often in individual models, you can get better sensitivity from, so for instance, you could still have the Z boson decaying, so the LHC, for instance, will produce, I think, about 50 billion Z bosons. And if you could really catch those, you can constrain it to about 1 part in a billion, whereas the Z width is not measured at 1 part in a billion. It's more like 0.1 or 0.01%. So that's a great constraint at sort of the most general level, and then we want to see kind of what else we can do with it. But actually, some of the leading constraints on dark photons up until LHCB put out a result recently was from Z measurements, precision measurements. Yeah, hi, Bo.
So when you talk about the current searches or the future search, you mainly focus on the, Atlas or CMS detectors.
Yes.
Could you comment on, people propose like new ways to new experiment setup to cheap, not so expensive search for non-limited particle and.
Yeah, absolutely. So for those who are not following this field, there have been proposed what we're typically calling dedicated detectors, which are essentially new components of Atlas or CMS that are located some ranging from 10 to hundreds of meters away, that are generally some version of like a box that the long-lived particle travels through and decays into. And there are a variety of these that have been proposed. One was actually recently funded by Simons and approved by CERN, which is called Phaser. And I would say that there's like 2 classes of those. One are boxes that are in the forward region, so like along the beamline. And that's what Phaser is. And what's nice about that is that most hadronic interactions are in the forward direction. And basically, as soon as they pass out of the detector, the the protons are kind of pulled in some other direction. So if you make a long-lived particle, it goes along the beam direction, but then the protons are pulled some other way. So you can put a bunch of cement or rock or whatever, and then put a box downstream and look for the decay there. And those tend to be very sensitive because the Atlas CMS and even LHCB detectors don't cover that region. So that's like very high impact. The others are more at larger angles. And you run into a problem, which is that for a particle to live, let's say, 100 meters or a kilometer to decay inside of the box, it has a very long lifetime. And so its probability of decaying inside the box is small. And you can actually show that the probability of decaying inside of Atlas or CMS is the same as decaying inside of one of those other experiments. So you don't immediately seem to win anything. Where you do win is that can be a bunch of shielding that absorbs the hadrons from the collision and makes it a cleaner thing. So I would say that the jury's still out about the benefit of them. You certainly can get a benefit in the background limited case, but we're also upgrading, well, not we, the experiments are upgrading Atlas, CMS, LHCB, and it could be that the new capabilities are such that they can reject a lot of the noise, and that makes the improvement due to experiments such as Methuselah still there, but not as big as they were. So I think there's motivation for them, but now it's really the nitty-gritty background studies of seeing exactly how much gain do you get from that. Any questions from the students or postdocs? You're all so shy. Okay. Okay, thank you very much.